But let me show you one case. Okay. This is a practical case where, for example, we know that V0 amplitude is 1, right? You send in a 1 volt positive traveling voltage wave, and somehow you have reflection coefficient of 0.3 in amplitude and a 30 degrees phase. Okay, so you do have some kind of reflection. So that is going to make the wave, the voltage wave on the transmission line, oscillating as a function of time, but for each location, you have different maximum allowed voltage. Okay? So what do I mean? What I'm trying to say is, so you have your load and you have your transmission line. If I really measure the voltage as a function of space and time, well, it's a wave. What's happening is the voltage will be clamped or formed or shaped by this standing wave amplitude. Okay? For example, your wave, your voltage is represented by the yellow stuff, right? Cosine is kind of changing. So the next moment, the voltage can be changed, but somehow the maximum value is limited by this white envelope. So what we just derived is the white envelope, but the voltage wave is the yellow trace, and it changes as a function of time. So this is telling you transmission line is really different from everything that we learned in the past. Right? Along the device, you will have very different voltage distribution. So we need to pay special care. Right? So I used to have a computer software which shows you a time varying wave, and it's clamped by the standing wave envelope. But now it cannot be played because Java is no longer supported. So I'll try my best. If I can recover the module, I can just show you again. Coming back to the PowerPoint. Along the transmission line, the allowed maximum voltage amplitude is space dependent. Okay, so at this moment, at this location, I can have the maximum voltage. At this location, I have the minimum allowed standing wave voltage. So it's periodic. So now the question is, from that mathematical equation, this equation, what can we learn? Do we only learn the derivation, or we can learn some physical meaning and remember it forever? What is the meaning of 2 beta d? Well, beta is equal to 2 pi divided by lambda, right? So when you look at cosine 2 beta d, 2 times beta d, which means when we have standing waves, the voltage, maximum allowed voltage as a function of space, is having denser or effectively shorter wavelength. Shorter by how much? Exactly 2 times. Which means maximum to maximum in the standing wave voltage amplitude is only having a length of lambda divided by 2. For your original wave, you have lambda. But now you have counter-propagating wave, so the standing wave pattern is shortened by a factor of 2. So that's the physical meaning of this 2, right? So this maximum point to the next maximum point is not distanced by lambda, but rather lambda divided by 2. So is the distance from the first minimum point to the next minimum point is also distanced by lambda divided by 2. Okay? So are we able to derive that? We derived this equation because we want to learn everything on the transmission line. So if given certain input voltage amplitude and we know the reflection coefficient, are we able to predict this voltage pattern everywhere? So that's a bigger question. We know its periodicity is lambda divided by 2, but are we able to precisely predict where is the first maximum located and where is the second maximum, first minimum, second minimum? That's a complete knowledge. All right? So take a look at this equation again. It's periodic. So how can we predict where the first maximum is? Or can we predict which location is the nth maximum located? Standing wave voltage maximum happens when this cosine takes the value of 1. Right? Cosine oscillates between -1 and 1. Right? So what is the requirement for cosine to be 1? The phases inside should be an integer multiple of 2 pi. So all we have to write down is d maximum. Let me use capitalized letter. Okay. So we are trying to find d maximum. So this 2 beta d maximum minus beta gamma should be 2 m pi. That's it. N is an integer, 0, 1, 2, 3, 4. Okay. So d maximum is equal to beta gamma. It's 2m pi divided by 2 beta. Okay, so that is so take a good look at the derived result. Are you satisfied? You should be, because as we predicted, due to the fact now we have the 2 beta d, it's making this cosine wave having a faster periodicity. So it repeats itself every lambda divided by 2, and that is exactly represented here. When you change n from 0 to 1 to 2, you have the next maximum location, and the separation, the distance between the 2 maxima is exactly lambda divided by 2. Okay? So how is this knowledge really helping us? As I said, we want to know everything on the transmission line. Okay? So for example, in this case, I already know that my reflection coefficient is 0.3 and having some kind of phase. So if on the examination I'll be asking you, I'm very nice, I gave you the reflection coefficient and its phase. And can I directly ask you, where is the first maximum located with respect to the load? Which means I want you to tell me, if I give you a load, what is this distance? From the load to the first maximum, are you able to know it? Do you have that knowledge? You should, because all you have to do is put m equals to 0. You already know this is 30 degrees, right? Let's just do it. D max 0. The first maximum is, in this case, m equals to 0, so you don't care about the second term. You only care about the first term. And theta gamma is given 30 degrees. So 30 degrees is pi divided by 30 degrees, 6. Right? Pi stands for 180 degrees. Divided by 4 pi lambda, so that is 24. Lambda divided by 24. So this means, in this given case, maximum is separated or distanced lambda divided by 24 away from the load. Okay? And then you add another 0.5 lambda divided by 2, you reach the second, the next maximum. Alright? So in that case, although we don't yet know how to solve for the positive voltage amplitude. At least, if this is given, we know everything on the transmission. Okay. So when we have forward and backward propagating wave, we have standing wave. So it's better for us to understand. In this case, if we have a matched line, which means ZL equals to Z0, you have no reflection. If you have no reflection, you have no standing wave, right? So therefore, the maximum allowed voltage along the entire line are having equal value. If you short circuit the line, meaning the load impedance is 0, or you leave it open, so the load impedance is infinite, both cases would give you a reflection coefficient amplitude of 1. That's a situation where you have the maximum variation in the maximum allowed voltage. Okay? So if you want to create the strongest standing wave, you either want to short circuit your transmission line or you leave it open. If you don't like to have standing waves, you need to perform careful impedance matching. So impedance matching will be the main focus next Monday, right? Okay, so now we can have some definition, because in the future, when you buy a transmission line as an engineer, do you want to repeat all this calculation again? Or do you hope the engineer who's selling you the transmission line can give you a quantified parameter so you know how strong a standing wave you can anticipate? So the answer is, people will give you the voltage standing wave ratio, VSWR. Okay? So that ratio is your maximum allowed voltage divided by your minimum allowed voltage. Okay? So in that case, if you take a look at the equation, the maximum allowed voltage is 1 plus gamma B, and the minimum voltage allowed is 1 minus gamma. So 1 plus divided by 1 minus. Okay? Now, a test to your understanding. If we have matched line, which means no standing wave, what would the standing wave ratio be? The voltage standing wave ratio. Matched. Matched means this is 0. So this S value should be 1. Okay, should be 1. This is the best transmission line that you can buy because 100% of the power is being delivered to the user. Okay, so you don't have reflection. You don't have reflection, you don't have standing waves. So this is the best transmission that you can hope for. But in practice, it's very difficult, right? So maybe you can buy some transmission line is spec with S equals 1.2, which is already great. So in the worst scenario, if the transmission line is shorted or opened, what would the voltage standing wave ratio be? Ask yourselves. In those cases, shorted or opened, as I showed you previously, the reflection coefficients for these two cases have amplitude, the absolute value of 1, right? So in the numerator you have 2, but in the denominator you have 0. So anything divided by 0 gives you an infinite value. So if you have the strongest standing wave possible, you have infinite voltage standing wave ratio. So this S value swings between 1 to infinite. Okay, so that's the reason why I said, if you can buy or you can make a transmission line to have an S value of 1.2, it's not ideal, but it's already excellent, right, as compared to infinite. So do we have questions up to now? I try to emphasize on the fact that once we have partial reflection, we will create standing waves. So I hope using those time, I was able to convince you voltage standing waves are giving some kind of new periodicity along the transmission line. The new periodicity is lambda divided by 2. But even though they are having voltage standing waves, we have the adequate knowledge to predict everything. Okay? So are there questions from the students at this moment? No? If not, I will use the next 10 minutes to really solve for everything on the transmission line. Okay? Essentially, we only need to solve for V0 plus. That's the only remaining unknown. So we only need to solve for that. We relied on the definition of the reflection coefficient, right? And we are now relying on these two equations. So the working philosophy is, if I know everything at the load, I know everything, right, at the load, I can just walk back until I reach the input point. And there's some knowledge that you already have. If I can stand at the input point and look to the right and view the entire load plus the transmission line as a new load, then I can have some equivalent model. Then I can formulate, or I can really calculate V0 plus. Okay? So the essence is I want to have a nice representation of the effective input impedance. Okay, so let's come back. Look at these two equations again. The first equation tells you the voltage phasor as a function of space. The total voltage is contributed by the forward propagated and the backward propagated voltage waves. And so are the currents. What happens if I directly divide the total voltage phasor by the total current phasor? V divided by I, by definition, is some kind of impedance, right? But in this case, this impedance is a function of space. Why? Because, as I mentioned, we have standing waves, right? The voltage, currents are all different along different locations. So if I perform a direct division, I now have a so-called wave impedance. Total voltage phasor divided by total current phasor gives you an impedance as a function of space. Okay? It's very messy, but you have the mathematical equations, so I'll skip the derivation. In the end, what you have to understand is the difference between the wave impedance and characteristic impedance. Characteristic impedance is a ratio of the forward voltage amplitude divided by the forward current amplitude, and the negative of the backward voltage amplitude divided by the backward current amplitude. But the wave impedance is just the total divided by total. Okay, it's just different. Characteristic impedance is a constant. It's not position dependent. But the wave impedance, ZD, is position sensitive, position dependent. Okay? So, as I said, if with that knowledge, at any location, I can divide the total V by total I can view the load plus a certain segment of the transmission line as a new impedance. So that's like Thevenin's equivalent circuit. 带为零等效应, right? Exactly in the same form. So all I have to do is at the input end, where my generator is connected to the transmission line. I started from the load. I start from the load. This is where I really know my backward voltage amplitude is. And then I walk for a length of L. I stop here. And I take a look back into the transmission line plus the load. And I ask myself, what is the effective impedance for the transmission line plus load? That's it. Z of D. And now you only have to replace D with L, the length of the transmission line. And that's it. Right? Just let D equals to L, and we should know everything. So this is what we're doing. Standing at the input end and looking to the right, which includes the entire transmission line and the load. That is my input impedance. So I want to skip all the mathematical derivation. I encourage you to work on your own. So the input impedance is nothing more than this VZ of L. Okay, eventually you can reformulate in this form. But once we know the input impedance, This is the equivalent circuit that we are working on. We have our generator, which is providing some kind of voltage. It has its own impedance, and then it's connected to this input impedance. The input impedance is the entire transmission line plus the load impedance. Okay? So, the generator intrinsic impedance is connected in series with the input impedance. So do you know what this voltage is? Voltage division rule tells you this VI is Zin divided by the sum of Zin and the generator impedance, and then multiplied by the generator voltage. Okay? So in the end, and that is known, right? V as a function of space, all you have to do is V of D, you let D equals to M. That's it. So in the end, finally, after all this complication, we know V0 plus. Okay? So I apologize for slightly going over time, but this is a better place to stop. So after all this trouble, we are able to solve for V0 plus. Once we have this V0 plus, we know V0 minus, and we know I0 plus and